Welcome to this explainer. If you've ever looked at a chemistry textbook and just felt a sudden wave of panic, hey, take a deep breath. Why stress when your big brother in science is right here? Today we're going to absolutely master chemical reactions and equations. I'm going to be right by your side breaking down every single concept so clearly you'll honestly wonder why you ever thought it was hard. We're going to take those dry, boring textbook formulas and turn them into a story you won't forget. So let's just dive right in.
Here's our roadmap for today. We'll be covering types of changes, balancing equations, combination and decomposition, the reactivity drama, double displacement, and finally, redox reactions.
Section 1. Types of changes. Physical versus chemical.
Let's start with the absolute basics. Look around you, right? The world is constantly shifting. You look different than you did 5 years ago. Well, in science, we categorize these shifts into two specific buckets. First up, we have physical changes. Think of melting ice, or maybe tearing up a bad report card. The shape or the state changes, sure, but the core substance, the water or the paper, is exactly the same. No new substance is formed. But then we have chemical changes. If you take a match and burn that report card, or if a piece of iron rusts, you're changing the actual chemical composition. A brand new substance is created. And honestly, here's a little mind bender for you. Sometimes both happen at the exact same time. Like when you light a candle. The melting of the wax is physical, but the burning of the wick itself, that's totally chemical.
So, how do you actually know a chemical reaction just happened? Well, just like you can instantly tell if a friend's mood changed by the look on their face, chemical reactions have telltale signs. You want to look for a change in color, a sudden shift in temperature, the evolution of a gas, like bubbling, a change in physical state, or the formation of a precipitate. And if you're wondering, a precipitate is just a solid that suddenly appears out of literally nowhere in a liquid. If you spot any of these, yep, chemistry is happening.
Section 2. Balancing chemical equations. The law of conservation of mass.
Okay, so when reactions happen, mass can never be created or destroyed. That means whatever atoms we start with as reactants, we absolutely must end up with as products, period. A completely foolproof method to make sure this happens is by mapping it out. You just list your elements, say iron, hydrogen, oxygen, then you count them on the reactant side and you count them on the product side. Now, looking at this example, it's a total injustice. We've got 1 iron to start with, but 3 at the end. To fix this, you don't mess with the chemical formulas themselves. No way. You simply add multipliers or coefficients in front of the compounds until the numbers match perfectly. Honestly, map it out like this every time and you'll never get it wrong. Section 3. Combination and decomposition. The chemistry of coming together and breaking apart. Now we're getting into the real drama, basically the dating scene of chemistry. Elements are constantly coming together to form new couples, or, well, they're breaking apart. And every single time elements interact, energy is involved. First, we have exothermic reactions. Exo literally means out, so these reactions release heat. If you take quicklime, which is the stuff used for whitewashing walls, and you mix it with water, the bucket literally becomes hot to the touch. It's aggressively releasing energy. On the flip side, endothermic reactions are the exact opposite. Endo means inside, so they absorb energy from their surroundings to actually make the reaction happen. A perfect example is plants absorbing sunlight for photosynthesis. And well, that brings us to the breakups. A decomposition reaction is exactly what it sounds like. A single combined compound is forced to break down into 2 or more simpler elements. But, relationships usually don't just end without a catalyst, right? In chemistry, to force a breakup, you have to apply energy. We usually do this in 3 main ways: by blasting the compound with heat, shining an intense light on it, or straight up shocking it with electricity. Let's actually talk about shocking it with electricity, specifically breaking apart water into hydrogen and oxygen. Students always forget which gas goes to which electrical pole during electrolysis. But I've got an amazing mnemonic for you. It's a funny little phrase, chal hat oye, which roughly translates to move away, hey. Just look at the letters. Chal starts with C for cathode and it gets hat, which starts with H for hydrogen. Then oye starts with O for oxygen and that goes to the anode. C gets H, A gets O. Chal hat oye. Trust me, you are never going to forget that now. Now, here's a classic question that shows up in exams all the time. Why in the world must a chemical called silver chloride be stored in dark, completely opaque, black bottles? Like, why can't we just leave it in a nice clear glass jar on the shelf? Well, the culprit is photolytic decomposition. If sunlight hits that clear jar, the light energy literally forces a breakup. The beautiful white powder of the silver chloride will absorb the light, the chlorine gas will just escape right into the air, and you'll be left with nothing but plain gray silver. And actually, fun fact, this exact reaction is the brilliant science that made old black and white photography possible.
Section 4. The reactivity drama. Who is the most powerful?
All right, this is where chemistry gets ruthless. In displacement reactions, it is a pure power struggle.
Strong, highly reactive elements literally kick weaker elements right out of their compounds. And to know who wins, we use this leaderboard, the reactivity series. Potassium up at the top is the ultimate heavyweight champion, and gold down at the bottom is the absolute weakest. Now, trying to just memorize this massive list from a textbook, incredibly boring and super frustrating. But don't worry, your explainer has a legendary trick for this that maps perfectly to the chemical symbols.
Seriously, read this out loud with me. Katrina ne car mangi alto zen Ferrari pirbi haya Q mili silver Audi. It basically translates to a funny story about someone asking for all these fancy cars but ending up with a silver Audi instead. But look really closely. Katrina is K for potassium, Ne is Na for sodium, car is Ca for calcium, Mangi is Mg for magnesium, Alto is Al for aluminum, Zen is Zn for zinc, Ferrari is Fe for iron, Pitterby is Pb for lead, High is H for hydrogen, Kun is Cu for copper, Mili is Hg for mercury, silver is Ag, Adi is Au for gold. Boom! You literally just memorized the entire reactivity series in like 10 seconds.
So let's apply that trick. Look at this equation. Iron mixed with copper sulfate. Is anything actually going to happen here? Well, think back to our phrase. Iron is Ferrari. Copper is way down below at Kun. Ferrari is obviously way higher than Kun. So, because iron is more powerful, it aggressively displaces the copper, taking that sulfate for itself. If you did this in a lab, you'd actually watch the blue copper solution slowly turn green as the iron takes over. Like I said, chemistry is ruthless.
Section 5, Double Displacement Reactions. The Great Exchange.
But what if both sides are pretty evenly matched, but they just kind of want to trade? Imagine two groups of rival sports fans constantly bickering. To keep the peace, they decide to just swap their friends so everyone goes home happy. In this type of reaction, we start with two completely clear, colorless liquids, like lead nitrate and potassium iodide. When you mix them, they don't just sit there. The ions seamlessly swap partners. The lead grabs the iodide, and suddenly, bam, a bright yellow solid instantly forms and just drops to the bottom of the beaker. This solid is what we call a precipitate. It's literal visual proof that a great exchange just happened right in front of you.
Section 6. Understanding redox reactions. Oxidation and reduction. All right, my focused learners, we have officially reached the final boss of the chapter, redox reactions. Now, people get very intimidated by this, but redox is honestly just a mashup of two words, reduction and oxidation. And here is the secret. They always happen at the exact same time. Let's strip away all the confusion and just look at the absolute foundation. Oxidation is simply when a substance gains oxygen during a reaction. It's oxidized. Reduction is the exact opposite. It's when a substance loses oxygen. Its oxygen supply is reduced. It really is that simple at its core. Gain oxygen, oxidized. Lose oxygen, reduced.
But, of course, here's where exams are going to try to trick you. They don't just ask what was oxidized. They ask you to identify the oxidizing agent and the reducing agent. An agent is something that causes something else to happen. And let me tell you, it is incredibly easy to overthink this and get the terms completely backward in your head under pressure. So I'm going to give you a foolproof, action-oriented hack to solve this instantly every single time. I call this the swipe trick. Step 1, you just look at the equation and confidently write down who gained oxygen and who lost it. Step 2, literally draw an X and swipe them. Just cross them over. The substance that got oxidized, boom, that is your reducing agent. The substance that got reduced, boom, that is your oxidizing agent. They are exact opposites. Do not overthink the logic during a test. Just find the oxidized, find the reduced, and swipe them. You're going to secure those points every single time. Just look at everything we've conquered today, from the absolute basics of physical changes all the way up to outsmarting redox reactions. You aren't just a student trying to survive a class anymore, you're legitimately a chemistry master now. When things get tough or distracting out there, and I know social media is always calling your name, just remember your goals. Stay focused, stay structured, and seriously trust that you have the tools to understand absolutely anything you put your mind to. But before I let you go, I want to leave you with one final challenge to really test your new mastery. Earlier, we discussed the electrolysis of water, right? Remember, chalha oye. We know that because H2O has 2 hydrogens for every 1 oxygen. The volume ratio of the gas produced is 2 to 1. But atoms weigh different amounts. So applying what you know, what is the ratio by mass? I really want you to think about that. Look it up if you need to and keep that curiosity burning. Thanks so much for joining me on this explainer, and hey, stay focused.
Thank you so much for watching. I'll see you in the next one.